Right. Okay, welcome everyone to this week's Non-Commutative Geometry and Topology seminar. It's my pleasure to introduce Frédéric Latrémolière from the University of Denver, who's going to talk to us about a geometry for the space of metric spectral triples. Thank you, Frédéric. Please go ahead.
So thank you very much to everybody, and nice to see you on Zoom, which seems to be my new way of traveling. It's so I'm going to enjoy Zoom Prague for about an hour, which is cool. Thank you very much to the committee for inviting me, and in particular Karen, who's communicated with me, and for this opportunity to talk. And so today I would like to touch upon a little bit some of the research I've been doing in so-called non-commutative metric geometry. And so I've been working on these issues of, sort of the metric aspect of non-commutative geometry, but from a particular perspective, which has been a bit of a niche that I've enjoyed, but I hope it will prove entertaining. And today I will take a new angle from my perspective, which is that I will actually mention spectral triple quite a lot. It's a fairly recent development in my work. So of course, the audience is very familiar with spectral triples, in fact, likely more than I am myself, but it's, I hope I will give you some aspects of these objects that maybe are less unusual, a little bit out of the ordinary as an entertainment for the day. So, well, let's start. So, what is a spectral triple? Well, that's an interesting question, which I will not answer. Rather, I will say that spectral triples, generally speaking, are this structure introduced by Kohn, technically in 1985, to discuss or encode information of a geometric nature over so-called quantum spaces, which means they are objects that are modeled after Dirac operators on Riemannian manifolds, but are vastly extended to include structures over non-commutative algebras. There are various definitions of these objects, and I will try to keep what I would call a core for them, things that seem to be common to most definitions, which is as follows. It's a triple given by a sister algebra A that I see as represented on a Hilbert space H. In this talk, for reasons to become clear soon, they will always be faithfully represented, so they can be identified really as a bunch of operators on the Hilbert space H. And my Hilbert space H comes equipped with an unbounded self-adjoint operator D, often called the Dirac operator for this, which has to satisfy essentially two properties. It has a compact resolvent, and it has this property that if you look at the elements of your sister algebras, which have, in so many words, a bounded commutator with D, which should have a slash through there, but does not, then this should be a dense star subalgebra of A. It is quite common, in fact, this dense star algebra is what people put as an A in the spectral triple rather than the, essentially the closure of it. But for our purpose, it makes more sense during this talk to simply take the closure and ask for a dense subalgebra. And typically, as you know, there are additional assumptions that are made to make sense of various constructions in physics. For instance, if you want to do some physical application, for instance, it's typical that you have some sort of summability condition, or geometry for that matter, some sort of summability condition on the spectrum of these operators that give you something to talk about dimension and so on and so forth. Additional structures like real structures or whatever, gratings, none of which I will particularly discuss. Some we could, and some not so much. But this common core of what a spectral triple is what all I need to develop the theory of today. So that will be sufficient. And as I said, they are, of course, a very common structure in non-commutative geometry. They're basically the basic element if you're going to do the spectral approach to non-commutative geometry. And they're also of some use, possibly in some aspect of mathematical physics, that I keep in the back of my mind as a motivation for some of what I'm going to do. Okay, so let me give you some examples of spectral triples. Now, of course, as I say, you have seen many, so I hope that the one I'm going to show you have the merit of being, if simple, at least maybe a little different than what we usually talk about for obvious reasons. One is a finite dimensional version that will be an interesting thing to keep in mind for this talk. So in fact, there are these two matrices. They're called the clock and shift matrices in dimension n, where clock is diagonal with roots of unity on the diagonal, primitive root of unity on the diagonal, and the shift is a shift. And those two unitary matrices, you find them every now and then when people talk about some aspect of mathematical physics. It goes from vile discussion of finite dimensional quantum mechanics to things in current studies of quantum field theory, for instance, where people want to look at these matrices as generating a sister algebra that is akin to a sort of finite dimensional version of what a quantum torus could be. They call that a fuzzy torus. So if you look at these two matrices, there's a natural commutational relation, which apparently I neglected to write, which is that SNCN is exponential. This Rn that I wrote here, CNSN. So they commute. They don't quite commute, but they commute up to a phase, and that phase converges to 1 as n goes to infinity. So that's the motivation behind the idea that eventually, asymptotically, that should describe a torus as n grows. But on the other hand, if you just look at these two matrices and you take their sister algebra, it's just n by n matrices. And so there's topologically, quote unquote, like the T for the seminar, I believe, is for non-Kuhn topology. Well, it's way overkill to say that, but anyway, topologically, this is essentially a space of endpoint. And what happens is you can turn it into something that looks like a torus. If you look at, and it's done commonly in physics, but commonly maybe is a big word, but it is a found description in the literature, that you can make a spectral triple over this that gives it a bit of a toral shape. And the idea is, as far as your Hilbert space is concerned, you simply take the algebra itself because it's a finite dimensional object here, a finite dimensional space. So it's just you can make it into a Hilbert space by putting the right inner product on it, which is the usual trace inner product. And then on the other hand, you put a Dirac operator, and the idea is that Cn and Sn behave a little bit like a position and momentum operators in this context. Because of this commutation relation I mentioned. And as such, you can sort of use one to define the derivative on the other by taking the commutator. So you differentiate along Sn by taking the commutator with Sn, and you differentiate along Cn with quote every time when you take the commutator with Cn. You want a self-adjoint operator, so once you self-adjoint 55 things, yeah, is there any question? Sorry, sorry for that. With Zoom, it's a little, you guess with sudden mics if there is a question. So if I do that often, it's a bad habit taken when I was desperate for students to ask questions for a year and a half on Zoom. It didn't work. So anyway, the point is that the Dirac operator that I've just wrote you can do variation, but is a fairly common idea found when dealing with fuzzy tori. And the justification to sort of look at this as a fuzzy torus is that it's as a torus and so on, is that we would like to really understand what happens when n goes to infinity. The justification for this is maybe meaningful, really happens when you let n goes to infinity. And that's going to be the theme today. So that's one example. The compact resolver and all that is of no relevance here. It's finite dimensional. Another funny example comes from fractals. So that's also one that is helpful for my talk today. So this is what's called the Serpensky Gasket, this little picture. It's a bunch of triangles, glued together. So it's really a collection of edges, right? I mean, each triangle gives you 3 edges. There's a whole bunch of those. And, it's nice. It's obtained as an attractor of some iterated function system with affine function, etc. There's many different constructions. For this talk, it is really helpful to look at it as a limit of graphs. So, and we'll see a picture of that soon. And you can also, again, people have been interested in doing geometry on this. There's actually quite a bit of research in different directions using different tools to try to discuss Riemannian geometry of that thing, which as far as, being a manifold is, well, it's not. It has, in fact, a fractional house of dimension. It's very irregular in so many ways, but
I think he may have frozen. I will send him an email.
Yes. So, perfect. So, okay, so there was this Serpensky Gasket. It's a bunch of edges forming this shape. What's interesting is that Lapidus and co found a technique to put a spectral triple on that. And it's actually a fairly natural idea. Basically, long story short of all the notation, which the intuition is more important than anything, is that you basically put a spectral triple on each edge. Okay, so you put each edge is an interval. There's a natural notion of spectral triple going on there. And we are, which I've defined for you here. I mean, it's kind of written the details, you know, you really put the derivative on basically the usual derivation on the circle. And then you represent each edge using the absolute value, you make it, you sort of symmetrize it. So you parameterize each edge by an affine function, you put a standard Dirac spectral triple, but you scale it so that it reflects the fact that those edges get smaller and smaller as time goes by. You just do the direct sum of those, and that's basically it. The magic of this is contained a bit in the representation, and even that is not difficult to describe, but it gives you spectral triple on this object, and it has nice properties. For instance, its summability is indeed related to the dimension, the Hausdorff dimension of this, etc., etc. So this is a natural spectral triple, and just imagine putting a spectral triple on each edge for the interval. So, okay, why would I care about those? Well, they both of these things raise a question, and the question is, you see, the first spectral triple on fuzzy torus, I really would like to know what happens when the dimension goes to infinity. And the spectral triple on the on the fractal, I would really like to know if it is a limit of spectral triples on naturally approximating object, because this fractal is a sort of limit of graphs. Is the spectral triple the limit of graph spectral triple or something? So that's sort of a natural question that I would like to address here. And the point here is that the point of this talk is to actually try and answer this question by saying, well, how do I make sense of this idea of sort of having a spectral triple that is approximated by another one? Okay, these are two situations I hope are vaguely illustrative of what I could mean by this. And to be fair, in physics, for instance, it's common that when people write something about this fuzzy torus, they take limit as it goes to infinity and claim that these are somehow representative of something on the torus, but there is no clear meaning of, besides, the dimension grew and it looks like it, of what that means. So the idea that I propose today is to put a distance on a large category, a large class of spectral triple. We'll describe that large class in a second, but it contains a lot of the examples you're familiar with. And I want a good and honest metric. So of course, distance 0 will not mean they're exactly the same. That's inconceivable, but that they are as much the same as I can make sense of at the moment, which is they are unitarily equivalent. So they preserve, there's a unitary going to the Hilbert space of one Hilbert spectral triple, to the other, which conjugate the Dirac operators and also implement spatially the isomorphism between the sister algebras, if I look at them as actually sister algebras on the Hilbert space. So that's a strong notion of isomorphism. And I would like to define a distance so that I can say, oh, look, it's true that somehow my fuzzy torus spectral triple I showed you momentarily do converge somehow to something on the torus. So how do we do that? Well, there are 3 ingredients I'm going to discuss that will help me do that. One is the metric given to me by a spectral triple that was in fact in the original paper of Kohn on 1989, which was in fact called something like quantum compact metric space in ETS, that there is in fact a naturally associated metric, and that's going to be the starting point of all my story. It's been for a few years now. And then we'll add to this the fact that there is actually a nice module structure underlying a spectral triple. Well, it's the Hilbert space with a representation of the algebra, but there's a little bit more structure to this. And last but not least, we'll have natural dynamics. I call it quantum dynamics because it is essentially an action by unitaries given simply by exponentiating our Dirac operators. And that will be the third tool. And putting together the 3 ingredients, which are not necessarily the one people look at most commonly when they deal with these structures, we will be able to, in fact, define a nice metric on spectral triple that satisfies 2 requirements. It has this coincidence property I listed here that two spectral pole will be the same under the, meaning this unitary equivalent if and only if the distance is null. And it will also give an answer to the questions in the red box as to, yes, there are limits to these objects that are described in germospectral triples. So that's the plan. And so if we're all cool with that, I will start talking about this first ingredient, okay? So my story really, starts, my little research in my little corner really is all about, has been mostly about quantum distances. And so the motivation for all that is found in this paper of Alain-Cohn. So if you give me a spectral triple, there is a natural distance that I believe is often referred to as a Cohn distance between any two states of your system algebra A, which is defined as written here. Distance between phi and psi is the supremum of the difference that psi and psi in absolute value, of course, the distance of phi of A to psi of A for A varying in your system algebra with this commutator with a Dirac operator bounded by 1. Now, the quotes around A are not a typo. That's because, of course, this commutator only makes sense on the dense subalgebra, which I don't want to give a name to. So this is defined densely on A, and that will do. And what Cohn observed in 1989 is that if you start from a very natural example, which really motivated, it would seem, the notion of spectral ripple itself, that is, it's on a compact connected Riemannian manifold with a spin structure, and you look at the, well, the spinor bundle. On this, there is a Dirac operator. And if you do the construction that Cohn suggests on the first box here, then you obtain a distance on the state space, which of C of M, which when you restrict it to the pure state, that is to the point of M, essentially, after identification, you get back the path metric induced by this Riemannian structure. So this is a way to recover some metric information. Okay. Oops. And that's really the first chapter of my story is I want to take this picture and enlarge it a little bit and say, oh, really what we're starting to do here is talk about quantum metric spaces. Okay, the notion of like, and Cohn suggests that it has to do with the metric on the state space. So let's generalize this picture to motivate a little bit my definition that's coming. So in fact, in so many ways, this Cohn distance in the case of a Riemannian manifold is a special case of a more general construction. So in that specific situation, and it's called the Monge-Convergence metric among many names. And it consists of taking a compact metric space. And you ask yourself, well, if I want to do downcut geometry, what I need to, of objects that look like metric spaces. One thing I want to do is encode that metric M at the level of the C-star algebra C of X. And the way to do that, that seems fairly canonical, is to take the Lipschitz seminorm that I remind you of right here, this quantity that's a seminorm defined on a dense subalgebra of C of X. Or it's a seminorm if you allow the value infinity, but it's dense, it's finite on a dense subset. In fact, dense subalgebra in this case. And you could ask, well, how do I, what's the, okay, L is defined by M, but can I recover by some sort of duality or something, the metric through my Lipschitz seminorm? And the answer is, well, there's this really nice metric due to, as I said, to Convergence in 1940s, which is sort of the dual metric associated to that norm in some sense, that I define here between any two probability measures. It's given by this nice formula where it looks a bit like the Cohn thing, right? You take the supremum of the absolute value of the measure applied to the integral for this measure applied to a Lipschitz function, Lipschitz seminorm 1 minus the other for the other measure. And it turns out that this metric has a lot of nice properties. It's very much used in various areas of mathematics, such as probability, statistics, and transportation problem, which was its original motivation, etc. It is also known under many names, but as all the names that I have seen so far, such as Wasserstein metric, Earth mover metric, and I don't remember many others, are all way posterior to the original work of Convergence. So, okay, so the relevance, maybe the first relevance, is that indeed this metric does allow us to recover from the Lipschitz seminorm the original metric in the following process. If you look at the space X and you identify it again as the Dirac measures at X inside the state space, then this map, which goes from the space metric space Xm to the state space endowed with this new metric here, that's Monge-Convergence metric, becomes an isometry. In other words, we recover the metric. So Lipschitz seminorm contains all the information I need in principle to recover the metric. And so that's a sort of and it's defined at the level of the C-star algebra. So as usual, now what I'm going to do is I'm going to isolate properties of the Lipschitz properties that are useful for my purpose, that allow me to develop an interesting theory, but still make sense when C of X is replaced by non-commutative algebra. So I can't refer to points anymore. I can't, I have to make a choice of what I consider to be important properties of the Lipschitz seminom. The more you assume, the more powerful your theory will be in some ways, but the less examples you might have. So it's a compromise. This compromise has taken a few years to emerge. I will present to you now what I think is I believe strongly is the current decent compromise. There is variation on the theme, but minor, of what we would now call the compact quantum metric space. So there are different names in there, and mine is kind of very selfish, but it's because this definition is strictly speaking from my paper, obviously, and I will tell you exactly what I added to that list. But it started with the idea of cone, where there was no topological consideration really on the cone metric outside of this specific example I mentioned. Then Mark had the idea, oh, well, if we're going to do that, we should have some sort of topological constraint, and then I added a little piece. So a quantum compact metric space is a pair given by, first of all, a unital C-star algebra A and a certain seminorm L, which I will often refer to as a Lipschitz seminorm because it's an analog of the classical picture I just described, which sort of shares a lot of the properties of the usual Lipschitz seminorm. So first of all, it's defined on a dense subobject of A. It's, in fact, I'm going to want a Jordan lead subalgebra, but of the self-adjoint part. But you can start with it's defined some dense subspace, okay, of the C-star algebra. It's a place to start at this kind of very surveyed nature of talk. And then what I want is, well, first of all, it vanishes only on the multiple of the unit because the Lipschitz seminorm typically only vanishes on the constant function. So that's the non-commutative analog of that. And then this metric I made a big deal about, which looks like a cone metric and the control-rich metric, and is constructed exactly along the same lines, which would recover, in fact, either of those for the right L. This metric must metrize the weak star topology on the state space. So the weak star topology on the state space, obviously, we are all functional analysts or people who have heard of functional analysis enough to know that this is a natural thing to put on this. It gives me a compact topology as well, which is quite convenient given I want to talk about compact quantum metric space. It's also actually the weakest topology this metric could possibly induce given the assumption I gave you so far. So that's a natural topology to put. It is indeed one of the reasons why the control-rich metric in the classical picture is so useful, because it does exactly that. So in probability, obviously, it's a metrization of convergence in the weak star topology. They call that weak convergence in probability, but that's what it is. So 1, 2, and 3 arguably are part of Cohn's definition, modulo technical details. 4 is really the idea that Mark added, which really started this whole story of compact quantum metric space as a whole little math corner. And then 5, which may look not like much, is my added thing. It's not, this obviously the Lipschitz seminorm satisfies things like that, but the idea is to add it as part of the definition because it's useful for something. So I added the Lamix property, which of course, everybody knows the Lipschitz seminorm satisfies in particular, but putting in the definition is something that happened actually surprisingly late because it's difficult to actually handle, and that's interesting. So I want, a Lamix property to hold. So normally you would say Lipschitz of the product is less or equal than the norm of one times the Lipschitz seminorm of the other plus flip the variables. But here it looks a little bit more complicated, but it's the same idea. It's just that since I insist for reasons that will become maybe a bit clearer later, to work on the self-adjoint part of my C-star algebra only in this definition, I need to make sure I take the real part and the imaginary part of the product, right? So that I fall back into my space. So that's a Jordan and the Lie product. That's this AB plus BA over 2, etc. So that's just a product, but adjusted to be in the self-adjoint part. And the upper bound includes that usual formula, but there are constant f and k. If f is 1 and k is 0, you get back the usual Leibniz property. It is helpful for some examples to allow for f and k to vary. So there is no particular reason not to do that. What is important, but I will not make a big deal in this talk, but it is a technicality that is actually quite relevant, but could confuse my exposition if I dwell on it, is that f and k should really be fixed for the rest of the talk. Like imagine you choose you have a bunch of examples, they all satisfy this for fixed phase F and K, and you fix that for the entirety of this talk, and we're never going to talk about them again. But we have to fix some. The last property is just the technicality. You want the Lipschitz seminorm to be lower semi-continuous on the whole of the system algebra A, which is maybe easiest to phrase like this. You have closure of the unit ball. Those properties are all shared by the Lipschitz seminorm. Okay, and this is sort of the list. So, it's a long list, but it's not that long. You just want to remember that if you do the cone-like construction, you get a weak start topology, and you have a Lamix property, and the rest usually is easy to remember. So let me give you some examples. Well, first, I won't spend long. The standard, if you give me a normal compact metric space, then there is a quantum compact metric space associated with that, which is, I constructed it 2 slides ago, given by the Lipschitz seminorm. It fits all of that. And in fact, this gives me an identification of the compact metric spaces as so-called quantum compact metric spaces, and I will, whenever convenient, use this identification implicitly. Infinite dimension, there is no longer any weak start topology and so on to worry about density and so on. So you end up with just asking for a seminorm with the right kernel and the right Lamix property. So there are lots of examples there. Here's a funny example. I won't dwell, but when Mark started this research, he in particular proved that one way to make a Lipschitz seminorm on a non-commutative example that is not trivial is like this. If you have an action alpha of a compact metric group G, and after averaging, if necessary, you have a length function that is distance from the unit from a left invariant metric on that G, then you can make something that looks a lot like a Lipschitz seminorm on the system algebra A on which alpha acts. And you can look at it, it's kind of the norm. You take A, you move it by the action, takes the norm of that, and you normalize by how much, how big G is. And so that looks a lot like a Lipschitz seminorm, and indeed it is, as long as it has the properties that its kernel, that is the same, that make L of A0 is exactly reduced to the scalars. So everything else, the weak start topology property of the associated most control-rich metric, etc., comes for free out of that. So there are many examples. I mean, and they've been studied in the literature quite a bit. But for the purpose of this talk, of the examples I'm interested in are those that come from spectral triples. So it turns out, unfortunately, at this point in time, it is unclear when an arbitrary spectral triple gives you a quantum compact metric space. There are certainly counterexamples. Again, the problem here is that what exactly is a spectral triple is a bit fluctuant. So, like, do you include some ability? Do you include existence of this and that? In cone reconstruction theorem, we have a list of properties that actually ensure that your spectral triple would be given by the Riemannian example I started this talk with, in which case, in particular, it would give you a quantum compact metric space, in fact, a classical one. So somewhere in there is hidden some properties that give you that, but it's not completely clear what they are. So in order to, I'm going to do what a mathematician in my position does. I'm going to define myself out of that problem by saying that a spectral triple is called metric when cone's metric induce a weak start topology. Or another way to look at it is I get a quantum compact metric space by setting LD to be the norm of that commutator wherever it makes sense. Okay, so are there examples of those that are interesting? Because we put a condition that is unusual on spectral triples here. And there are examples. So in, again, that original paper of Alain Cohn, one idea that he proposed to make a spectral triple was to take a discrete group, a length function on that discrete group called L here, and you look at G as represented on L2 of G the usual way, left regular representation, and you define your Dirac operator, quote unquote, as a multiplication operator by this length function. And Alain Cohn proved that this was indeed a spectral triple. That's defined a spectral triple. It takes some work. It's not completely immediate, as it is often the case, in fact, to establish that this gives you example of metric spectral triples. So with the right sort of the code metric is well behaved topologically. This is given, but there are examples. So hyperbolic groups fit the bill. That's a work of Riffel and Ozawa 105. Nilpotent groups fit the bill. That's a lot of Riffel and Michael Christ of 2015, I believe, or something like that. So those are examples of metric spectral triples that are interested. It includes a whole bunch of examples already. In 98, Mark proves that the usual spectral triple on quantum torus are metric. So by usual, I mean, you have your quantum torus, you represent, let's say it's a 1 on 2 generators, you represent on L2 of the torus, and you put the actual Dirac operator on the flat torus there. It actually also gives you a spectral triple on the quantum ones. And they do have the properties that if you look at the cone metric, it induces a weak star topology on the state space. And the other properties that are easier to put, weak star topology is where the meat is here. And we have Jens in the audience. So I would be remiss not to point out that Jens and my former students, and now I realize I think I forgot someone. How do you pronounce that? K-I-E-D. I heard it in your talk, Jens, and I realized I was going to mispronounce it terribly today if I said it, but he's also a co-author there. Sorry, I forgot.
No. So David was not part of that paper from.
It wasn't. I was not wrong. Okay, good.
Yeah,
sorry.
Yeah.
Good. I was suddenly terrified. I forgot an author. So on record, on camera, recorded for life. I was studying to carrots. So this is very serious stuff. So Dabrowski and Sitas had a spectral triple on the published fair actually, and it gives you an example of a metric one. So those are nice examples, and it shows that this is a non-vacuous concept. And none of these proofs are particularly easy per se. So that's, there's a call. This is not, oh, I look at spectral triple proof, it's automatic by any means. In fact, the techniques used for each of those are different. None of them, and there are even different ones on the quantum tori that I haven't mentioned that are of the type of the previous box, the cone recipe, as I call it. So yeah, there's a whole family of those, and none of the proofs that these things actually are metric spectral are the same. Okay, so whatever. There are two examples I could have written, but slides, I didn't want to make another slide for that. I gave you two spectral triple at the beginning of this talk, a finite dimensional one and one on the fractal, and both of them are examples of metric spectral triples. In the case of the finite dimension, there's not much to say. In the case of the fractal, it's interesting because a cone metric restricted to the space gives you back the geodesic distance on that space. So that's actually, again, a nice thing that people in fractal geometry would be concerned with, the actual intrinsic distance on the space. So what I want to do, well, I started this talk with the idea that I want to make convergence of these things. So as a first step, I propose we make convergence of the underlying compact quantum metric space. If you have a metric spectral triple, and this is the class I'm going to work with from now on, then it gives you a metric. And I could ask, well, is there a natural way to make compact quantum metric space converge to each other? That would be a beginning, a pseudo metric on my spectral triple, and in particular, and it's not T, it's Z, typos. The reason why you would actually want to do that, well, I mean, I learned that when I was a PhD student back then, but why Mark started this idea of talking about quantum compact metric space was very much motivated by this idea of taking the distance between them, or rather to talk about convergences of such things. And that's because in the world of metric spaces, there are natural ways to do that are already available to us. Namely, in particular, I will focus on this Gromov-Hausdorff distance. So Z, not T, Hausdorff distance, first of all, is a way to tell you how two closed subsets of a metric space are far apart there. Sorry, for me, it's an absurdly early time in the morning. But so if you take two close subsets of a compact metric space, there is this thing that I just wrote, which I'm sure is familiar. You take the distance from from a point in one to the other, and you soup over all of that, and you do it symmetrically, and it gives you actually a nice distance. But that's only making sense. You have two closed subsets of a fixed compact metric space. So what we want is, when we're going to work with compact quantum metric space, that we're never going to have a compact quantum metric space as a subspace of anything. It's a standard problem in geometry, right? To be a subspace means to be a quotient, and very often, I mean, think about quantum tori, they don't come to you necessarily as quotient of anything naturally or intrinsically. That's not how we approach this. So you want a sort of intrinsic version of the Hausdorff distance between compact metric spaces with no explicit reference to an embedding. And this idea, it turns out, is due to Gromov and Edwards in the reverse order. And the Gromov-Hausdorff distance here is the idea is that, well, you take two arbitrary compact metric space. They don't live anywhere in particular, think two manifolds, and you don't want to choose a particular isometric embedding or anything. They just live there. And what you do is that you secretly embed them into a compact metric space at random, and you calculate the Hausdorff distance between these two isometric copies there, and then you take the infimum of that over all possible compact metric space embedding. So the idea is that in practice, what you do is that you're going to say the Gromov-Hausdorff distance is smaller than alpha if there's some space somewhere where I could embed x and y, and there the Hausdorff distance is alpha or less. Okay. What's remarkable is that this is indeed a distance. It's even a complete distance up to full isometry of the spaces. So distance 0 means the spaces are isometric. And so there is a whole, it's an industry, it's a whole field of which I am again tangential for going non-commutative. But in the classical picture, Gromov introduced that as part of his study of virtually nilpotent groups. He was using this, actually was using the locally compact version of this, but let's put the details out there. For when working with Cayley graphs of groups, etc. But then it became also a very prominent tool in Riemannian geometry and so on. So that's a very useful and very interesting object to which a single slide will not do justice, but it is the motivation for what I will do next. So I would like to do this, but for compact quantum metric space. Okay. So in order to do that, I need to tell you what an isometry is. All right. So first, as a passing remark, to begin with, before I'd say an isometry, a Lipschitz morphism, that is what would be as a natural morphism of a category of compact metric space, is easy to define. It's just one definition is it's something that preserves the domain of the Lipschitz seminorms. And among all those Lipschitz seminorms, so it's probably, it's trivial with the definition to check this as a category. So that's also a nice aspect of that, which I haven't, done anything with, but notably quantum compact metric spaces form a nice category. It may not be so obvious to me what a category of spectral triples are. I gave you an equivalence, so I kind of know what it means for them to be the same, but what a morphism between them is, I think, is not entirely clear. You can have a lot of ideas, but which one is the right one? The quantum isometry, so it's a particular example of a Lipschitz morphism, but it's a star morphism in particular between the underlying C-star algebras in your quantum compact metric spaces, but it has to also sort of preserve the metric in some sense. So ideally, you would phrase this by saying that if you take your star morphism between A and B, it's actually my next little box, I can start there, and you do this dual map. If you look at the bottom here, there's a spy star, which goes to, the usual dual map, and you restrict it to the state space. Well, now it's actually a map between actual metric spaces, right? Because the whole point of the story is that the L seminorm thingy, the Lipschitz seminorm analog, induces an actual metric, a good old metric on the state space. And so you could literally ask for that to be an isometry. It is more convenient to phrase it at the level of the seminorms, and Mark Riffel did the work for us. You end up with this condition that a quantum isometry is a star surjection, is a star epimorphism, surjective star morphism, such that if you look at the LB, the Lipschitz seminorm on the codomain, it's a quotient of the Lipschitz seminorm on the domain. Okay, that's what this blue box says. It's a quotient, and that's really, in fact, rephrasing a theorem of McShane that says that in a classical picture, if you have a subset of a metric space and you take a real valued Lipschitz function on that subset, you can extend it to the whole space. When you do so, typically you will increase the Lipschitz seminorm because the Lipschitz seminorm is a supremum, you do it on a larger set. But McShane proved in 34 that for real valued Lipschitz function, you can do it. You can find one extension that has at least one, there's really many in general, that has the same Lipschitz seminorm. And so that's exactly the statement here. You can only grow by, because if you take an element in B, then you can sort of lift it to an element of A without extending its Lipschitz seminorm, okay? But that's a non-commutative version. And it does give you a genuine isometry between the state spaces for the Morse convergence metric. So we have a nice notion of quantum isometry. It does form a subcategory to the category that I described with Lipschitz morphism. That is, you can compose this thing and everything. And it also tells me what two quantum compact matrices being the same for all intent and purposes means. And it means that there is a full quantum isometry, which means that the mat pi is actually a star isomorphism, and you have the quantum isometry property both ways, which degenerate to it. It's an isometry for the Lipschitz seminorms as well. Okay, so far so good. Not any question. I haven't lost all my audience yet or anything like that. We good? Okay. I'm still on Zoom. I have Karen on my other screen. I'm on Zoom twice now because I've learned my lesson. So I'm staring at Karen to make sure that she moves, and so therefore I am still alive. Okay. It has happened to me, anecdote for a pause, but it has happened to me once at the end of a class. I think it was a linear algebra class, whatever, during the COVID here, where I was online. And for 5 minutes, I talked to myself because the students, of course, were never, ever asking questions. The last 5 minutes, my internet at home dropped. And I was just finishing my discussion and nobody, and then you're like, oh, luckily the recording said it didn't happen for too long. So that was funny. Okay, so back to the Gromov-Hausdorff thing. So here's a picture that's easier than writing a definition here. So suppose now I give you two quantum compact metric spaces, A and B. Here they are. And that's the one at the bottom of that triangular thing. And I want to define a distance between them. So what Gromov suggests I do is embed them into an arbitrary, isometrically, into an arbitrary quantum compact metric space. That's my D. Of course, all the arrows are now flipped. So embedding means this in this vocabulary. Pi A and pi B as the quantum isometries I just defined. So the quotient of LD through pi A is LA, etc. In particular, keep in mind that if you look at the reverse map, the map pi A star that goes from the state space of A to the state space of D by duality, then it becomes an isometry for the underlying non-structural H metric. So what you can do is, again, following the prescription, right, is to take the Hausdorff distance between isometric copies of the state space of A and the state space of B within the state space of D, just like we did with actual metric spaces, except you can't quite do that. You can, but you won't get a metric, as far as I can tell. So there is a reason, and the reason roughly is non-Coulomb geometry is hard, and it's not things are not abelian anymore. So there's a whole bunch of stuff I can't do. So basically, what you can't do here is throw away points you don't need. It's not that easy. Truncations don't work as well. So you end up with having to be a little sneaky. And instead, you take this Hausdorff distance between the state space of A and the whole of the state space of D, the whole of the state space of the thing you embed into. So in the classical picture, it's like if you took the Hausdorff distance not between X and Y instead of Z, but between X and Z and Y and Z. Of course, that, dominate, you can use that as to make an obvious bound on the distance between X and Y, since Hausdorff distance is indeed a distance, but it is a bigger number. Okay? I'm going to call that the extent of my tunnel. Also note that now takes the distance between state spaces, not just points. There's no point to speak of anymore. So it's a different construct, but similar. So it's still there. What is the dual propinquity? Well, it is my non-Coulomb analog of the Gromov-Hausdorff distance, and therefore, unsurprisingly, I would say, it is indeed the infimum of all these numbers you can make for any possible embedding you can come up with. Okay, just the same idea, but this is the number it takes the infimum of. Propinquity is due to the fact that, in fact, this idea of doing a non-Coulomb analog of Gromov-Hausdorff distance has a long history. Mark Riffel started that in 2000 when I was just beginning my life and a grad student. And he called it the quantum Gromov-Hausdorff distance. It was natural at the time, but it's defined in a different setup. In his world, there is no sister algebras, there are order unit spaces, so it's more general that way. But there's no multiplicative structure, no Lamix property. And that actually affords you a lot of flexibility that I don't have anymore by working on sister algebras. But I, on the other hand, I am a big, it's my own perspective on this. It's completely, how could I put it? It's a quirk if you want, but I really want to live inside the world of sister algebras. I do because I believe very strongly that the fundamental allegory of non-Coulomb geometry is that I replace, an algebra of function by an non-Coulomb algebra. If I lose the algebraic property, well, I mean, sometimes you do, like order unit space, operator systems, etc., come up, of course, in this area. But I feel that you have to have a good reason to do that. Like it's somewhat of a change of paradigm a little bit, or at least it's a stretch. And so I really want to try to avoid it if I can, like to stay within my algebraic picture as much as I can. And this is in fact secretly where the Lamix property becomes essential in the work. So there were a lot of other people who tried to address the fact that Mark Riffel's construction had a bad, well, not bad, but had an incomplete distance zero property. So in order for me to explain what I mean in words, this construction I just did give you a complete metric on the class of quantum compact metric spaces up to full quantum isometry. So it means distance zero here is very nice. You do have a star isomorphism between the underlying sister algebra and you preserve the quantum metric, okay, as I explained in the previous slide. So the star isomorphism bit is what's, if I gave this talk 5 years ago, would have been a huge deal. It was new. In Mark's distance, for instance, since you don't have multiplicative structure, you can apply his distance to sister algebra as well to the self-adjoint part of, but what you get is an order isomorphism. You don't get necessarily something that extends to a star isomorphism. And various attempts to fix that have been made, Very often, though, you had some trade-off. You lost the triangle inequality, or you kept that, but you lost completeness or something. So this seems to be a situation where we stay within our nice category and we get the right coincidence property. The metric is complete as well, just like it's the Gromov analog. So Cauchy sequences do have limits. But now talking about the classical analog, you remember that quantum compact metric spaces do embed into the world of quantum compact metric spaces. Sorry, did I say quantum twice? I don't know. The classical embedded the quantum. And so it's now we have two metrics. We have the actual Gromov-Hausdorff metric, and then we have this thing I just defined that you can apply through this embedding. And you could ask, well, how they're related. And you don't expect them to be equal at all. It would be a miracle. I mean, I involved the state spaces. I did this weird thing for my extent, which wasn't quite just the distance between the two spaces, etc. So we don't expect them to be the same, but it turns out that they are topologically equivalent. So we really did, in fact, extend the Gromov construction to the non-period realm, because in practice, it is the topology that it induces that we care about, much more than the actual number, which we usually can't calculate. So we have succeeded in extended. So technically, if you do that and you apply because of time, if I just keep the non-spectral triple example, there are many examples. I just had a few just to entertain us, but let's refocus on the spectral triple. That is my main topic. If you look at this fuzzy tori I introduced, then you can ask, oh, well, does the compact metric structure induced by those spectral triple on fuzzy tori with this bunch of commutators converge in the sense I just defined to something on the actual torus? And the answer is yes. So I need to tell you what the spectral triple at the limit is. That's a bit of a cheat, really, because I only need the metric induced by this, but I'm going somewhere with that. So here is a spectral triple on the torus, a little bit of a weird one, and you will have to apologize the barbaric calculus notation, d theta and d phi. I hope it makes sense. There's a sub-Lf derivatives, but basically it's a derivative in the direction theta and phi. So you get this kind of like Dirac operator. That's not the standard one because of these sort of this thing is not flat. It has coefficients, if you want, in front of the derivations. But it is actually the limit in the metric sense of these spectral triples considered in physics on the finite dimensional system algebra driven by the clock and shift matrices. And you can see what happens. The commutators become this derivation times the scalar functions. Okay, and you recognize the cosine and the sine as a real and imaginary part. I made a comment that we needed to work with those. That doesn't change at the limit. So, by the way, there is a much less pleasant to write version of this, which involves limits that are non-commutative. So it's not restricted to the two case and the commutative limit. You can actually make finite dimensional versions of Dirac operators that converge in this sense to actual quantum tori in general. But it is technically much more involved. So I will skip the details. So this is an example of a convergence that's quite non-trivial. What about my Serpensky gasket? So I told you there was a picture. Here we go, not too early. My Serpensky gasket is a limit of graph system algebras. And so I said, well, really the spectral, remember the spectral triple on the limit thing, which is a little black thing at the end there. It's really just a sum of spectral triples on each edge, okay? Just scaled appropriately. So if you have to have a spectral triple on the graph that approximate that, which are these pictures with more and more triangles, there is an obvious thing to do. You truncate, right? I mean, you stop adding edges when you don't have them. And yes, it does work. That is, if you put the quantum metric associated with that truncation on the graph, you simply have, spectral triple scale appropriately on each interval, then you get the convergence. Now, this result, I make a comment. This result is, of course, because here we have a million objects. This is really a result about normal metric spaces, because I told you my metric, my propinquity thingy is topologically equivalent to Gromov-Hausdorff distance in the case where we deal with a classical picture. It's not immediately clear. You deal with there's a subtlety here that this Lipschitz seminorm, which I remind you, Lipschitz seminorm for a spectral triple is the norm of the commutator. The fact the norm of this commutator in this particular construction of the Serpensky gasket does give you a Lipschitz seminorm in the usual sense for an actual metric is not systematic, but it is true. And in fact, it gives you the Lipschitz distance for the geodesic distance. We proved that in there. Well, for the Serpensky gasket, it was known. we check it's also true for the graph. And so this is actually a convergence in the sense of Gromov-Hausdorff of the graph thingies in the geodesic distance toward the Serpensky Gasket. Interestingly enough, I believe it is new. I asked Michel. This is a result I did with Michel Lapidus and one of his students, Thérèse Landry. And I believe it's a new result. Even there, it's not a revolutionary result. It's hard to prove. But it is interesting to know that this is the geodesic distance is not the one you're seeing in the picture. Right? This is not an isometric embedding of the geodesic distance into R2. In fact, I have no idea what where I could, embed this isometrically to make a picture. So this is interesting in principle. But since time is passing, if you apply it to spectral triple like I just did, it gives you partial information. Okay, it gives you the cone metrics are getting close to each other. This is quite concrete, quite nice, but it doesn't give you a distance where distance 0 implies the spectral triple are the same. It just tells me the cone metrics are the same. So how do I make it? So it's a little bit of always a rush now in the talk, but I will try to give you the idea. What do I add to make this into a metric? So I start from there and I want to add stuff. So there are other ingredients I mentioned at the beginning of my talk. One ingredient is the module structure, if you want, given by spectral triple. So your spectral triple has a Hilbert space on which A acts. So that's actually a kind of module. It's actually H as a Hilbert space is also a module over the complex numbers. It's a Hilbert module over the complex numbers, which may seem way overkill, but it will be useful in the next slide to keep that in mind. And there is an extra ingredient, which is this operator. So the first thing I'm going to do is I'm going to pass to a norm. I'm going to take the graph norm of this operator. And this structure, so this, this algebra A acting on H as a Hilbert module over the complex numbers with this new norm has a bunch of properties. Here are the properties it has. So the box on top is that structure, the Hilbert module, this graph norm. I remind you of it, the C star algebra acting on the left, which comes as a bonus with a metric, given by this quantum metric, but it's the norm of the commutator, and then C and 0. So that is because of the literature that I keep the notation I use in my papers, but the C and 0 may seem a bit redundant here. C is because it's a Hilbert module over C, and 0 is because the only quantum metric on C, which is really the continuous function on one point, would be given by the Lipschitz semi-norm 0. So at the moment, this is an example of a more general structure, which is a metrical C-star correspondence. It's kind of like a quantum compact metric space, but you add a module. So just like if you have a manifold, which is a Riemannian manifold, there are vector bundles over that, which are nice Hermitian vector bundles. They have a metric on top of being vector bundles, and there is all sort of compatibility properties. So that's the same idea. Here I look at my module as a Hermitian module, the section of a Hermitian bundle over the A if A was a continuous function, a manifold, but I extend this widely so that it now makes sense over any compact quantum metric space. And I keep only some information. So what are the information? Well, as I say, M is a C-star correspondence. So it's on the one hand, it's a Hilbert module on the right over B. And on the other hand, it's a left module over A, and the whole thing is a bimodule. And A really is acting as a star representation of A into the bounded operators, some adjoinable operators on M, etc., etc. A and B are given with quantum metrics, so everything is metric now. So they're not just C-star algebras; they actually come on top of it with a metric. And then D, which is in the case of spectral triple, the graph norm, has a bunch of properties. In general, like the Lipschitz semi-norm, I keep what I need. So it dominates the usual norm. The reason why I do that is because, okay, so let me give you a quick bunch of sentences that may not make a ton of sense because it's a little technical, but my original example wasn't from spectral triples. My original example was motivated by Riemannian geometry. D was essentially the norm of the connection seen as an operator between appropriate modules. So D came from metric connections, okay? And in general, of course, well, when the kernel of a connection is not a trivial question, it's not like with the Lipschitz situation where, well, those are constant. So it's easier to take the max of the connection norm and appropriately define seen as an operator and the usual norm and get rid of that zero, when is this 0? So that's that. That's the first point one. Point two, which is in red, is the actual analog of asking the Monge-Contour-H metric to metrize a weak star topology. Instead, I'm asking for the unit ball 4D to be compact. Why is it the analog? Because essentially RZ-Ascoli theorem. Okay, so that's the analog. And then there's a bunch of Lamix property. We don't need to lose sleep over them. Those encode the fact that if you have a metric connection, we can take the derivative of the inner product, or the inner product with a connection. If you put norms and everything, you get some sort of Lamix property. This is what those things do. Okay? So it turns out what's important for today is that if you start from a metric spectral triple, so the metric qualifier is important to get a quantum metric on the C-star algebra, but that's it. As far as everything else goes in this slide, it's gone for free from being a spectral triple with a compact resolvent. The compact resolvent is what gives you 2. Lamix properties are just because of the algebra. So these properties are satisfied in particular by spectral triple. And then this slide is horrible, and I need to really rethink how to write it, and I apologize, but let me give you the idea of the slide. So you give me, now I'm going to define a distance between things like, sorry, all right, come on, don't crash again, things like this. So the distance is defined not between spectral triple quite yet, that's the last slide, and I think I may be running out of 2 more minutes or 4 more minutes, or I do not care. Oh, I don't hear you because you are muted.
Yeah, take your time. You crashed, so I think everyone.
Okay, just a few. I'll try to be quick and leave people ask me what I meant in questions, but I would like to give you a little bit of an idea. So here's the thing. It's difficult, you know, you could have this idea, these two spectral triples, and I want to embed them in some weird ways into a third spectral triple, right? I mean, this would sort of be mimicking what I've done until now, but that's hard because it forces you to construct a new spectral triple, which you know, can't do. I mean, in general, it's asking way too much. So what I do instead is abstract myself. I don't really need to embed my spectral triple into a third one. I rather take a spectral triple, associate one of those things I just wrote, which gives me a lot more flexibility because now I don't have to work with the Dirac operator. I just work with a weird norm. And there's lots of ways to make weird norms much easier. And I define a metric on those in the same model as I did before. So it's technical, but it's not as horrible as it looks. I apologize, my computer was falling asleep. It skipped 3 slides. So bear with me here. My tablet is not being my friend today. Usually I'm a Linux guy, so I will say that next time I bought a Microsoft product. So the idea is, is to do a tunnel. So if you remember, and I could try, the idea is you had 2 quantum metric spaces, you embed it into a third. Well, now I have 2 of these horrible C-star correspondences with metric. So the C-star correspondence, right? So you have a module over 2 C-star algebras on left and right, and then everybody, the C-star algebras and the module, have some sort of additional norms or semi-norms. And what you do is you simply ask to embed means you find a third one of those, and the 2 ones you were given are quotients of that third one through natural morphisms. And the morphism of a C-star correspondence, it's 3 maps, right? You have a map between the module and a map between each of the C-star algebras, and the map between C-star algebras are star morphisms, and there's a natural commutation relation, change of basis to get module maps. I mean, really, if you wrote the definition, you would come up with it. It's a natural thing. There's no magic. The only additional thing that I ask is that since I have quantum compact metric spaces, my star morphism should actually be quantum isometries. So they should have these properties that the Lipschitz semi-norm quotient through them. And I have the same property on my module map, which is this thing at the bottom. That is the D norms, these norms that I introduce on my module should be the quotient through the module map of the D norm on the on the space in which you embed. Remember, all the arrows are flipped. So if I embed into a space, it really means that I'm a quotient of that space. So there is a notion of tunnel, and it's really the same idea. You just ask a bunch of quotient maps, of quotient norms, and it takes the infim. And this is a funny thing. I don't need to define a new extent. So if you have a tunnel like this, it's a tablet, I can write on it, but I'm really terrified of crashing this thing now. So if you don't mind, I'll just say it verbally. Well, let's see what I can do. Let's experiment and see what happens. So we have, your module, a new module, and it's subject on module 1 and module 2. And what that really means is that, in particular, this is a module over, say, A and B. Okay, so let's do the A part, the same for B. So you have did I call it A? I didn't give it a name. I call it D. And D must surject on A1 and A2. And then you have a B scalar field. That's a scalar field of your module P, which is a Hilbert module of a B. And that, surject on B1 and B2. But let's focus on the A picture. So you have D for surjecting on A1 and A2. Right? You have B is a Hilbert module. It has a left action of this algebra D, and it is supposed to surject on two of those weird metrical system correspondences. One as a left action of an A1, and the other one as a left action of an A2. And D, A1, and A2 all come with quantum metrics. And I'm asking explicitly in my definition somewhere here, that these two maps from D to A1 and 2 are in particular quantum isometries for the respective quantum metric structure. So this thing gives me a tunnel in the sense of 6 slides ago or so, right? And similarly with the B, so I have these tunnels for free. And what you do is you take the extent of this, the distance between the state spaces, etc., the extent of this, the distance for the state spaces, etc., and this is what I call the extent of my tunnel. It does not involve the modules explicitly because it's actually rigid enough that everything I want to know about the distance between the D norm is encoded entirely. That's kind of cool. So it turns out that you have, it takes the distance between state spaces of various sister algebras. The modules come along for the right. You don't need to do anything with them. You take the infimum over all possible such graph, such embeddings, and it gives you a metric. And it's actually, again, a complete metric on this metrical sister correspondence up to, okay, what's a full quantum isometry? It's what you guess. It's two such metrical propinquity. Let me go back to my definition. So two correspondences with all this data are quantum isometric when there's an isomorphism that's also a full quantum isometry between the A's, between the B's, and there is a linear bijection between the modules that's on the one hand preserves the Hilbert module structure, on the other hand, is compatible with the action as well of A. I mean, everything is compatible, and all those D, LA, and LB are preserved by these maps. So the whole structure is preserved.
Frédéric, sorry.
Yes, please. Please.
Can you go back to that slide again with the metric C-star correspondence? I'm just, is there really no condition on the right action of?
There is, it's down there, the point number 4.
But that's the left action, right, of A.
Oh, the right action. Yes, you're right. Yeah, so it's because, so for what I do, it turns out that you have to remember, so yes, it's essentially, the answer to your question is it's kind of hidden inside of 3. That's right, that's kind of all I need. So what happens is by preserving the inner product, it turns out that you will preserve the left action as well, the right action as well. Yes, it's kind of hidden in there. I was surprised too. So the first time I wrote the paper, there was a condition, and it was exactly like 4, but with the right action. It looked like 4, but on the right.
That's a semi-norm on B is Leibniz in some sense also.
That's exactly correct. Because of the Lamix property, you get it for free, which I did not notice in the first paper on this, the 2016 paper. There would be an extra condition that I removed later because it turns out it's redundant. I did not observe that at first. And it is exactly because of the Lamix properties that you can get it back through this, because of the connection between the Lipschitz norm on B and which, the action come from that and the inner product. So it turns out it's enough to get the distance 0 property. So yes, it's surprising. It surprised me too, but it's a very good question. But it is in there. It's hidden behind 3. By the way, it turns out it's useful to remove it, because it turns out sometimes you don't have it actually. So
So yeah.
Did it answer your question? Are we good?
Yes.
Perfect. Thank you. Yes, that's a very good question and a very good point. So we get a metric, and since I'm late very much, I'm going to give you the quick story. So, okay, so if you get a spectral triple in particular, you can apply this metric to it. And yes, of the examples I told you, the Serpensky Gasket and the fuzzy torus, they would converge. It works. However, it's not completely the whole story, because you preserve the D norm, the graph norm, but you don't necessarily quite preserve the D. Essentially, you preserve the absolute value of D, in essence, your metric property. So luckily, I will spare you the details, and I will promise you it's 2 minutes, 1 maybe. How do I finish? I make it covariant. This is something I've been doing for a few years, that you can have covariant versions of this metric. The word is bad, but I'm sorry, that's a title I use, so it's fixed now. But what I mean is, you have, even for quantum compact metric space, you have just forget the module structure, just a compact metric space, and you have a group acting on this in a nice way. Can I not only make the compact metric space converge, but the whole group action converge as a dynamical system? And the answer is yes, you can do that. It's actually kind of fun to do. Okay, and you can do that also on modules. It's a bit, there's a lot of letters, but the idea is natural. And when you have a Dirac operator, here is the action I want to consider: the action of R by isometry on the Hilbert space, right? I mean, it's a natural quantum dynamic. It's a nice action. It preserves the denorm, so it fits nicely. And what you do is you throw in one more number on top of the ridge. And this is a covariant version of the ridge, of the extent. Sorry, the extent, not the ridge. This is a covariant version. So the covariant means, instead of just asking, sort of a state to be close to another state, you're asking now for a state to go along for a little piece of orbit and be close for that whole little piece of orbit to another state following a little piece of orbit. You have two actions, right? So you can move your states around, but you want the same state to move. You take phi, you should have a psi on the other end, so that when you apply the action on the C algebra for a little while, psi moves and psi moves and they stay close. Okay, that's the natural idea. In the world of modules, it's a little different, but it looks exactly the same. It's like this. So there's a lot of soups and infinite. It looks horrible, but I put some notes. The red part, this first bunch of soup enough, is just a Hausdorff distance type. So it takes a soup over one set of the inf of the other. Then the green part is what I just said. You want things to stay close for a whole little piece of orbit. The bigger, the better. So 1 over epsilon. So the small epsilon is, the longer I want the estimate to work. And then my action, ut is my exponential action of my Dirac operator. So uj is exponential of one of the Dirac operator, uk is exponential it, the other Dirac operator. And you just want to follow them for a while. How do you measure closeness? Well, you have to work through some details, but basically it's a sort of Convergence distance, okay? So this is what the orange part is. You take these two things, these two states, and the state that they define, you measure the Convergence distance using this sort of module equivalent of the Convergence distance. So it's complicated, but natural. And if you do that, good news, you get actually a metric on spectral triple. If you throw that, so you take your extent and you take that number, you take the max of those, you do a little bit of gymnastics, but basically that's the idea. Poof, you get a metric of between spectral triples. And done the same way, for every time you have an embedding, you do this calculation, you take the infimum over all possible embedding of the extent and this calculation, and you get a metric, the normal square root of 2. These are technical difficulties I don't want you to worry about. It's something that doesn't matter too much for this talk. And it turns out that you can apply the spectral, this distance to two spectral triples. So in particular, it gives you the conversion of the metric. It's included in there because of the construction. I mean, it just comes from the fact I told you that a tunnel between C-star correspondences give you in particular tunnels between quantum compact metric spaces. So it dominates the metric one. It actually dominates the one for modules because it's built using exactly the same idea as I did for modules. You just added this action. But by adding this action, what I gain is that now I do have the distance zero means that my spectral triples are unitarily equivalent. So that gives me the whole picture. Can you possibly prove anything with this? Yes, and this will be my conclusion. This example I started the talk with, the fuzzy torus, it does converge in the sense of this metric to the Dirac operator on the torus that I list here. So you do have, it is possible, and there's one more slide, but we'll skip it, that simply says that it works with the Serpensky Gasket as well. So we have an actual metric on spectral triple, which is distance zero when you want it, and we have actual non-trivial examples of convergences. As I said, this fuzzy torus business can be extended to non-commutative limits at the cost of higher technicality. I am just finishing a paper right now about the properties. Okay, now I take the problem backward. You have a bunch of spectral triples that converge to a spectral triple form metric. What can you say? And actually quite a few things about the spectra and so on. So it preserves spectra and some semi-continuous for this metric, for instance. That paper will be on the archive within 2-3 weeks. I just need to finish polishing it. So this is a nice metric, it turns out, but I will stop by telling you what the metric is, and there are examples of convergences. This one and this one work just fine. And sorry, I went over time. I abused the fact I crashed. I feel a little guilty, but I apologize. Thank you very much for your patience.
Thank you, Frédéric. It's very nice and informative talk, and no worries at all about the running over time because you did crash. Thank you.
You're welcome. Thank you very much.
Are there any questions?
I can ask a question, Frédéric. If I mean, in this result you had, I mean, it's super nice. Is that what happens with completeness?
Yes, I knew someone was going to ask this because it's the hard question. So what happens with completeness? So there are good news and bad news. And there is I think I know how to fix the bad news, but it's not done yet. Okay, I mean, that's hopefully between now and next year with teaching in between. So let me give you the good news first. The good news is that the metrical version and the covariant metrics in that case are complete. So if you ignore the spectral, you take a sequence of spectral triple, right? And then you make this construction. It takes the module that it gives you, and it takes the action that it gives you, and you apply the metric, and you ignore that where it comes from, just to this data. That is complete. So if you give you a Cauchy sequence, it will have a limit, and what the limit will look like is a module over a bunch of sister algebras with an action of R by unitary by isometry on the module. Now the question is this action of R on the module from the Dirac operator? And even if it is the norm on the module the graph norm of that generator? That part I do not know. Okay. In general, I do have a conjecture. Please don't prove it before me, although okay, you might. But my conjecture is that you need to strengthen a little bit. So it's basically one of those usual problem of analysis. I think it's not. At least that's the way I look at it. Yeah, this thing. So basically, what happens is this: if you want convergence, if you want to be sure that your limit is going to be the right thing, so it comes from the right thing, you need secretly a converse of generators, right? So you need a first order condition to this. So what you would probably end up doing is not just look at this expression, but replace UTJ by UTJ minus the identity divided by T.
Okay. So you say,
which makes sense. And then it will work.
Over the derivative to some extent also.
That's exactly correct. Convergence of the derivatives is needed to get convergence of the derivative. Because, I mean, it's the usual problem, right? If I don't have, if I just have convergence of the function, not the derivative, I'm stuck. So there is a stronger variant if you want completeness. So I think what happens is I intend to write this paper. I do think it works. Okay, I've checked it on draft that if you replace by what I told you, and the paper will look like this. If you have a Cauchy sequence in the sense of the metric I just discussed, and there's this extra condition, rather than define a new metric, I find it more convenient, then you would have that it works. Because the metric I gave you has already a lot of built-in completeness to it, but there is a slight subtlety that the limit may not be a spectral triple. And that's actually, I think in general, you know, there should be counterexamples. I feel that you could have spectral triples, but imagine the spectrum become like denser and denser. See what I'm trying to say? Like it's a discrete spectrum, but you put the eigenvalue closer and closer and closer and closer. Maybe the action converge, but there's no hope to really have a compact resolvent thingy at the end. But you still have an action because the action itself doesn't care. So you see where I'm going with this, right? So I think that it
could be semi-finite or something like that. I mean.
Exactly. You're going to have some sort of, you're going to lose. It's not going to be horrible. You have leftover. So you're going to have and it's actually a very common situation in the Gromov-Hausdorff world. So even though I made this metric much stronger than the usual one, I still expect that you're going to have some sort of singular space arriving sometime at the end, but it won't be completely singular. There'll be leftovers. There'll be something a bit like a Dirac operator because you have an action. So you'll have a generator. It may not have compact resolvent, and the norm that you get may not be its graph norm anymore, but some affiliated thing.
Thanks a lot, Frédéric.
Does that address it?
Yeah.
So that's a really, that's a deep question. So I noticed when you gave your talk, a couple of things. So one thing is, this is for spectral triple. Of course, we want to be able to, so yeah, there was this compact resolvency. So the compact resolvent is important in this work. So to extend it to say modular things, that you made me think about that. You would have to work a little bit. I mean, the modular, whatever you call it, but the twist or the theta or whatever you call the twisting would have to be involved. in there. And because if you don't have compact resolvent anymore, then the graph norm does not do the trick because it doesn't give you this compactness of the ball property. But I'm optimistic that using the modular structure, you might recover something. And I know I had other comments from your talk, but I don't remember. But yeah, okay. So I mean, you made I think you talked. There were questions about, okay, if the Dirac operator converge, I mean, sorry, if the structure that you described, it wasn't a. If the structure you described, the modular, the spectral triple converge, in the metric sense, the question was, what can you say about the actual Dirac operator? I mean, is there any information you can extract from that? And I think in general, if you just have the metric one, the answer is kind of no. You get information on the metric, and that's about it. But if you extend it to this, then it becomes interesting. And I think someone did ask a question. Well, if you had a sequence of your spectral triples and then converge, in your talk, it's a riffle metric, if I recall, but let's say now they converge for this metric. Can I say something about the limit, about the compact resolvent? And the answer is no, not yet, but the paper that I will have on Spectra maybe step in that direction. And that's exactly related to your completeness question. So, I mean, I think that there is somewhere within a few months of work or 6 months of work, because there might be actually some result to the effect that under additional strengthening, yes, you would be able to conclude that the limit has compact resolvent. I mean, it's nice. It's an actual spectral triple. So I think this relates to a question you had in your talk. So I wanted to bring that up. Mm-hmm. Anyway, so sorry. Is there any other question that sorry. Yeah.
I'm going to ask a question. I was wondering, maybe you said this and I missed it, but what does convergence of the spectral triple look like at the level of the spectrum? I mean, so naively, if one had a realizable Dirac operator, the spectrum, how would it look at the level of the eigenvalues? I mean, would it be convergence at the level of each eigenvalue?
So that's a paper I'm just going to put on. So that's why I didn't make a big deal out of it. It's I have a nice 40 pages draft on my computer I need to clean up, which should show up in the archive in about 3 weeks. Let's say 3 weeks. It has to be, because then I start teaching again. It better be done with the paper. And it will answer your question in the positive. The spectrum converge in a certain sense. So you have to make sense of what I mean by this. But actually, it turns out that a lot of things do converge. The bounded, there is a way to make sense of the statement that the bounded continuous functional, what is it? The bounded continuous functional calculus on the spectral triples converge, if you see what I mean. So there's a way you take a function in CB of R, bounded continuous function on R, apply it to, you have a sequence of spectral triples, DNs, and you apply F to DN, that gives you a bunch of operators. There's a way to make sense they converge, actually, in a strong sense, to F of D. And from that, you can deduce that indeed the eigenvalues of the limit are limits of sequences of the eigenvalues of the spectral triple. Yes.
And might this be equivalent? I mean, if you had convergence of the eigenvalues.
No, it's not equivalent.
It's not equivalent.
Well, first of all, I mean, at the bare minimum, you have so you have more. Under mild but very reasonable assumption, you'll have convergence of multiplicities too, for instance. So right there, you have a multiplicity issue. And the second thing is, it's not because there's much more to this. So, I mean, I would have to cook up a counter example that I'm going to fail horribly. But basically, for instance, if you just had, one of the things that's underlying here is that you don't have just a convergence of the spectral, of the Dirac operator, so to speak, in some sense. You really also have convergence, for instance, of the quantum metric on the underlying C-star algebra. And it plays a role because the extent is calculated from that. This is kind of disconnected, right? I mean, if you just give me a spectrum, I can take Hilbert space and just make a diagonal operator with that spectrum. And here you go. It has nothing to do with the C-star algebra A of the spectral triple part.
Sure, sure, of course, yeah.
So that's where it breaks. And it's, in my way, it's actually nice, because if it just converges to the spectrum, of course, it would be a lot of ink for. But it is very common in physics. That's exactly what they say. So in the physical world, what happens is they do these operators, and they somehow. They don't. In the paper that's going to come in the fuzzy torus, you see this guy, this operator dn. Someone calculates the spectrum of that, and I'm very thankful for them for that, because this is sort of thing that for me is difficult. But physicists are very good at that. They actually have the spectrum of this. And it's kind of helpful that it's finite dimensional, because the way they do it is they kind of guess the eigenvectors. I mean, they have this habit with this kind of ladder method to figure out, oh, I have a good idea of what the eigenvectors are going to be. They plug in, solve an equation, works miraculously. And because you have the right amount, poof, you have your spectrum. I don't know how to calculate the spectrum of this thing at the bottom. I'm sure, people who do elliptic operators would be able to do that. But for me, this thing with all the gamma matrices to calculate the spectrum of that seems nightmarish. But I can do it now using this result that I just mentioned. I actually do know what the spectrum of this is now by just taking the limit. In the physics world, what they do is they calculate the spectrum of dn, they take the limit, and they don't claim it's a spectrum of d necessarily, but that's what they kind of really strongly want. So for them, that's what it means to converge these models, typically, right? Because, I mean, if you believe in spectral triple in physics, then you believe in the spectral action, right? So they kind of say, well, you do the spectral action calculation at the n level, you take a limit as n goes to infinity, and it should tell you something about what happens at the limit. Now, the paper that is going to come out, but which is directly based on this convergence, tells you that these claims do have substance. There is indeed convergence under good assumptions. So it's stronger, right? It includes a spectrum of convergence. Yes, that's the answer is yes. And I'm very happy about that. It's bad construction because you kind of have this. This is convergent. This is mimicking a convergence of the semigroup, right? You could have tried the resolvent too, but this is better to work with this because they're nice isometries. And yes, you preserve the spectrum. Well, you don't preserve, sorry, it's continuous in a sense, yes. But it's more than that. It's more than that. You have convergence of the whole action. It's more than that. That's right. It's stronger.
And then what about something like the spectral dimension?
Yes, so that is more difficult. So what happens with spectral dimension is it's essentially a convergence result. So you immediately see we have a bit of an issue because in the finite case, the spectral dimension will be 0. No matter what I do, right? dn here has spectral dimension 0. And it will converge to, well, nothing, 0, right? I mean, there's no hope of, so it's more complicated. You have the convergence of spectrum, but the summability is like looking at the partial sum, right? And yeah, you have the question of, those are finite no matter what you do. And then you want to look at them as partial sum of a bigger series. Essentially, you have your series at the end that you want to converge, a sum of the lambdas to the s, where s is your summability level. You want this thing to converge. Well, you have to look at the behavior on the finite levels. Does that make any sense? So it's not like there's nothing because you have convergence of the spectrum. So you can look at how your spectrum is evolving. And under certain conditions, you might be able to say something, but it's not going to be continuous. The spectral dimension is not going to be continuous because you're low finite dimensional approximations. So right there, the spectral dimension in and of itself dies. There's no hope of getting something. But it's not completely, I don't know, this is all very fresh in my brain, but it's also very new. So you have to be able to say something, right? Because you do have the spectra of each of the dn as you go along. So you can see kind of how the eigenvalues are starting to evolve. And so you can maybe do some estimation of what the limit dimensions or on some sort of lower bound or something on that. But you're not going to get continuity. And that's okay. So that's because I'm a metric guy. That's, as I say, my little niche of the normal world. So in the metric world, the Gromov-Hausdorff distance is really, it's kind of interesting. It's really a metric concept, not a topological concept. When we teach topology, we often say, well, a metric space is just a way to get a topology. I mean, it's a nice way to get a nice topology. But it turns out what I really liked when I was a student is actually when you do the Gromov-Hausdorff thing, is you're really working with metric. It's actually not so much a topology because indeed, you have complicated space limits of finite spaces. So the topology is kind of like treated badly by the Gromov-Hausdorff convergence. And that's similar to this, right? The dimension is a topological concept. This being said, I want to point out that under very natural assumptions to avoid weird coalescence of things and so on, the spectral actions converge for this metric under natural. So you don't have the dimension, but you do have some things that are of the same family. So traces of things converge. because it just, some. So there ought to be a way to get something out of that. But the spectral dimension is a hard one, just because it's as I say, if you go from finite dimensional approximation to infinite object, obviously that shows that there is some limits of what you can hope to preserve. But there must be something left, but I don't know what it is.
Okay, thanks a lot.
You're welcome.
Could I ask, are there spectral triples over other fractals? For example, like the mega curve, something like this, that you might be able to access?
Yes, so there are some. The class that Lapidus, so the expert on that is Michel for me. That's my go-to person for fractal. We started a collaboration on that, and we intend to continue that. So the answer to your question is, I think that it's largely the one that I'm aware of that works are largely this one-dimensional thing. So if you, so the certain fractal, the fractals in question are made of lines, curves. Okay, so is there a big union of curves? That's what they can do. So they have, I don't know, like what do you call that? The circles, Apollonian circles would be a bunch of curves that you can apply this story to, for instance. If they're 2D, so like the 2D version. I mean, not what I mean in 2D. Sorry, it's a bad vernacular. What I mean is you do the same as the Serpensky Gasket, but instead of edge triangles, usual triangle, you do that in 3 dimensions. So you remove a whole block. You can do a similar construction, and you'll have faces that are 2-dimensional if you want. That is not done. So it's essentially those made of lines that people have studied. And this is 2014, this work of Lapidus on these fractals. And actually to do it for nice fractals that live in 3D, like your sponge and so on, that is not done yet. So the answer is no, we do not know yet. We certainly expect to, but it is not done yet. So there is much more to be done on the fractal side. It's kind of a new angle for me, but I'm very excited about that. So yes, it's a very good question. So there are more fractals under the Serpensky Gasket, and the collection is, I mean, this is described in the 2014 paper of Lapidus and his former student, what the class here is. As I say, things like Apollonian circles and things made of curves, but not things that are higher if it's made of, so they're IFS, but they end up being a collection of curves with some nice properties. So yeah, there's much more to be done there. So there are, because I've noticed in the fractal world, a lot of this work is done on Serpensky Gasket. Same with the approach with Dirac forms and so on. That's also a lot of the time Serpensky Gasket and affiliates. So there's much more to do on more general fractals. So the answer to your question is yes, there are more examples, but not too many. And this is a super interesting area to explore. Absolutely.
Thank you very much.
Oh, and I should say, maybe it's optimistic of me. It's probably completely optimistic of me, but we had this question about completeness, and I did mention that in the paper. One way you could dream of making spectral triples on fractals is by using this technique. That is, you build it on finite objects that approximate your fractal, and then you take a limit, and you hope that somehow it goes somewhere. So that's maybe a new way that hasn't been explored yet of getting new spectral triples. That would be the dream. I mean, it's more, my motivation was more physics maybe, but I think for fractals, it's also super interesting. Sorry for that interjection. But
no. But that's an interesting point, because as Karen has been pointing out in the chat, this manga curve is a limit of certain graphs. Is it bipartite graphs that it is? Something like this. So that's why I thought, since it's built out of these one-dimensional things, it might be something accessible.
That's right. That's right. So this is the idea, but yeah.
Thank you very much. Yeah.
You're welcome. Yeah. So I mean, there's much to explore in this. This is all new and fresh. So I actually know precious little about this, to be totally honest. But I'm quite happy that this example suggests, indeed, you're absolutely right, that there's more to that, and that might be people should investigate that. Yeah.
Okay. Are there any more questions? Okay, well, if not, I see. Of course, Karen's going to share the talk for next week. Ehud Meir from Aberdeen who will be talking about interpolations of monoidal categories by invariant theory. All right, so I guess that's thank you again, Frédéric. And
you're very welcome, and thank you to all of you for your patience and for the great opportunity. It was very nice to talk to your group. So thank you.